Welcome back. Previously we saw how to find the locations of these peaks, how to find the indices of the peaks, and we found the value of the period by taking the median of all the periods that we measured, and we found that that was about 0.747 seconds. Now, what we'd really like to see, our next step in analyzing this data, is what is the rate of decay of these peaks. And I can see that there's some curvature here as these decay. As we've discussed previously, this is exponential decay, not linear decay. So how could I come up with a function that would fit that rate of decay? Well, first let's look at what the rate of decay looks like. So we'll make a new figure, and let's plot plt.plot t of peaks and x of peaks. And we see here our exponentially decaying amplitude. This is just the envelope of our oscillation. It's the shape of the outer variation here. How do these decay over time? I see that they're decaying from a little more than 0.3 to a bit less than 0.28. Here we see the same thing on this graph. And what we'd like to do is generate a function that fits this decay. Now, I'm not sure how to fit exponential decay, but what I do know how to fit is a polynomial. So there's a function I can use in NumPy which fits a polynomial to data points. And that function is called polyfit. I want to fit this data with np, that's numpy.polyfit, and this tells me that the way this function works is I need an x value, a y value, and a degree. So if I'm fitting a linear function, my degree will be 1. If I were fitting a quadratic, my degree would be 2. And you know, if I have a linear function, it'll look like y equals mx plus b. M and b are two outputs which define that linear function. If I had a quadratic, I would have something like ax squared plus bx plus c. So I'd have three outputs, a, b, and c, that would define the function. So let's call these outputs a and b. A comma b equals polyfit. Those are the two things that will be output by my fit. And the thing that I want to fit is this data that I've just plotted, t of peaks versus x of peaks. And remember, we want to fit that with a polynomial of degree 1, in other words, a linear regression. But notice this isn't linear. This isn't varying linearly. So to undo exponential, what is the opposite operation? What's the inverse function of exponential? It is log, np.log. And in Python here, log naturally means natural log, the best kind of log. So np.log is the natural log of x of peaks. If we have exponential decay and we fit the log of that y value, y variable, then we will be fitting not decay like this, but linear, a linear function. Just to check that that's the case, let's duplicate this function. Let's make a new figure. I'll just select these two commands and make a new figure. And we'll do plt.plot t of peaks and np.log of x of peaks. Let's use black squares. K is for black. Since blue is already taken by B, we use the last letter of black. And I can see I've still got some curvature here. Why is this happening? Why am I still getting curvature? I remember now what I forgot to do. To come back here to my data, x. And what is x oscillating around? I see it's oscillating around 0.26. So if I tried to fit this to an exponential decay, well, it's not decaying to 0. It's decaying with an offset. So let's fix that by going all the way back and adjusting our x array here. So after I've defined x, I'm going to take x and let x equal x minus x dot mean. So now I've subtracted the mean from x, and I see it's oscillating not around 0.26, but oscillating around 0. We'll rerun each cell here. I see I'm graphing here, and a constant offset in my oscillation is not going to affect my velocity. Velocity is the same regardless of the point that I oscillate around. Rerunning each cell here. No change. No change there, but now that we've shifted to unbiased data oscillating around 0, I should see that I get, and indeed I do, linear data now. So this is exponentially decaying, and we can interpret the y-axis here as the exponent of the amplitude as it decays. Now remember that a and b are the slope and the intercept. A is the slope and b is the intercept of our fitting function. So adding a plot to this function, we will say plt.plot t of peaks, and then we want to transform that array to a times t of peaks plus b. And let's let that be red. Hopefully that'll show up clearly. We forgot the a. We'll say a times t of peaks plus b. Here we're off by some factor because we haven't rerun this cell. Rerunning it again, and then rerunning this, we see that now our red function is fitting really well this decay rate. So we have found that the rate of decay, the slope of that, is this constant a, so negative 0.02, negative 0.028, it's almost negative 0.03. So what does this mean? This is the e-folding time of our decay. So 1 over 0.03, or 1 over 0.03 is about 30. This means that the oscillation will decay to 1 over e of its initial value in about 30 seconds. We can see we're starting at about 0.042 here, decaying about 30 seconds later to about 0.02. So that seems about right. We're decaying to about 40%, 37% of our initial value over a time of about 30 seconds. That is what we have found with our constant A, the decay rate there. This is the constant that we've been calling gamma in our analysis of decay.